Alright, so in this problem, we have an insulating cylinder shell of radius 3 centimeters that has a uniform linear charge density of 25 nanocoulombs per meter. Alright, so we have a line of charge, and we know that lambda is equal to 25 nanocoulombs per meter. Alright, so one probe of the voltmeter is placed on the surface of the cylinder. So we have one probe here, and we want to know at what distance from the center of the cylinder would the second probe need to be placed for the voltmeter to read 85 volts. So somewhere up here, so RB equals question mark, our voltage is equal to 85 volts. Alright, so we're looking at a potential difference due to a cylinder of charge. So we know that potential is the work per unit charge to move the charge, a test charge, not an actual charge in this problem, from here to here. But in this case, we're not dealing with point charges, so we can't just do KQ over R. We have to deal with the fact that this is a distribution of charge. So we have to understand how this charge is affecting the environment around that. And we do that through the electric field. So as I have written up here, we're going to use the idea that the potential difference is equal to the integral of the electric field dot dl. But notice this is a dot product, so we need the path that is parallel to the electric field. So since this is a cylinder of charge, we are looking at the concept that the electric field is going to come off of the surface. And I'm assuming it comes off and not goes in because it is a positive 25 nanocoulombs per meter. So we're going to draw our Gaussian surface so the edge is along our point of interest, so wherever RB is. So when we go back to Gauss's law, we're going to plug in 2 pi r times L is equal to Q enclosed over epsilon naught. And then Q enclosed over L is going to be our linear charge density. So we are left with the relationship I have plugged in up above. So our linear charge density divided by 2 pi times the electric constant times R. So notice because R is what we call this distance between where the electric field emanates to where it's going, so our DL is actually dr in this case. So that's why I've replaced the DL over here with dr. And I don't have to worry about the dot product anymore because this R and this R are parallel to each other. So then I can do the integral, and the integral of whatever R is the natural log. And I can then plug in my values. Remember to convert the 25 nanocoulombs per meter to coulombs per meter by multiplying by 10 to the minus 9. Plugging in the electric constant, so the 8.854 times 10 to the minus 12. So that gives me a distance of 3.62 times 10 to the minus 2 meters. So this diagram probably isn't even really drawn to scale. It's a really tiny distance. So a tiny distance above the surface of the cylinder, given that the radius of the cylinder is 3 centimeters, and we're only talking about 3.62 centimeters. So it's important to remember that we can use the electric field for a charge distribution in order to calculate the potential difference. We're going to continue to do that throughout the semester. And remember, this DL is the path that is parallel to the electric field. So you can establish what variable you need to use besides the DL when you integrate once you plug in the electric field equation.